Well, welcome to panel 8 of the International Space Medicine Summit. This program is on spaceflight and automation, although Steve's going to change the title just a little bit when he speaks. This is always has been in the past, we've done this before, and it's a great panel because you really often get varying perspectives where crew members are a little more interested in having access to the buttons and other people are more interested in HAL 9000, running things and more automation, particularly things that would need to occur all the time, like on a long space flights. This panel is headed by Dr. Steve Robinson. He had a BS in aeronautical engineering from UC Davis, and then got a master's and doctorate at Stanford in mechanical engineering. He became a co-op at NASA in 1975, and I got to figuring out that was 47 years ago, Steve, so I can see the gray hair now. He spent 36 years at NASA working at various centers. He was at Langley and Ames, and then at JSC, became an astronaut in 1994. While he was an astronaut, he flew on 4 shuttle missions, and probably one of the braver ones, and the one where he did some interesting things, was STS-114, which was the flight after the Columbia accident, and there was so much concern about heat shields and that sort of thing, and he had to do an EVA to go out to the underside of the shuttle to do a little adjusting of some batting and things on the shuttle. He went to academia in 2012 at UC Davis, and he is head of their spaceflight research program and also directs the Center for Human Robotics, Vehicle Integration, and Performance. All that's real good, but the most important thing about Steve is his love for flying. He really likes to fly, whether it's low and slow or in jets, and a lot of us in this business think that's a really good deal. So take away, Steve.
Thanks so much, Dr. Jennings. Boy, it is good to see you again. Richard and I go way back. I don't know how you know all that stuff that you just said, but thanks very much for the kind introduction. And yes, I absolutely love to fly. That's never changed in my whole life. And I think that goes for many of you here. We have an amazing panel here today. And yes, indeed, we've changed the name of the panel a little bit to call it Human Spaceflight and Autonomy. We have a very strong panel here, starting with Captain Bill Shepard, former astronaut, Dr. Ali Anderson, professor at CU Boulder, Dr. Sandra Stankovic, research professor at Harvard, Tamer Barkouki, Air Force Reserves PJ and PhD candidate in UC Davis, Dr. Katya Akia, a professor at MIT, and Captain Jim Weatherby, astronaut, who will be joining us a little bit later. Okay, let's start. First of all, let's talk about what autonomy is. And this will not be a formal definition, this will be a working definition for today. If you don't agree with it, then please speak up and tell me what your point of view is. The way I think about it is automated systems execute pre-programmed behavior. Autonomous systems are able to engage in unprecedented, unplanned decisions and actions, depending on how they're implemented. And for spaceflight, my opinion is we always want humans involved with autonomous decision-making. These humans could be onboard crew, could be in mission control somewhere on Earth, or in a control center in a surface base, the lunar surface, or potentially Mars in the future. I think these humans act as gatekeepers for anything that is going to be done that is safety critical and what isn't safety critical when you're doing it in space. So I refer to these systems as semi-autonomous, reminding us that humans are always involved. So the point is not to replace humans, to augment humans' performance and safety. So with that informal definition on the table for discussion, I would like to first introduce Captain Bill Shepard, former Navy SEAL, an aerospace, ocean, mechanical engineer, and NASA astronaut who, among many other accomplishments, served as the first commander of the International Space Station. I remember being in Star City when Shep and his crew launched, and it really seemed like the beginning of an era, and sure enough it was. It's 23 years ago now. And Shep, I have a question for you, like I will have a specific question for each of our panel members. And for you, my question is, for near future deep space operations. What's the best way, and by best I mean safest and most efficient way to allocate responsibility between humans and autonomous systems on the spacecraft? How do we decide when to allocate tasks versus plan for collaborative teaming? And you can take it from there, Shep.
Well, Steve, it's a big question, and I guess one of the things that is kind of bothersome for me about your definition of autonomous is if you have machines that are doing unplanned. I'm going to get to the answer to your question, but it's going to take me a minute to get there. So please indulge me. If machines are doing unplanned things, my question for the architects is, can these unplanned things be exactly repeated? In other words, are they determinate? And can humans understand after the fact what the machine did or what the machine is doing? And the thing that bothers me the most about where I see AI going as a technology, as I understand it, in many cases, those aspects of the technology are not going to be transparent to the human. And I think this is incredibly bad. So backing up to your question, before you can allocate responsibilities to machines versus humans, you have to have a topology that lays out the landscape of what it is you're trying to do. And on the International Space Station, we started a functional hierarchy, and we did that system by system. And in many cases, the way that these machines are built, the physical and cyber capabilities are kind of smeared across a lot of different parts of the station to create a single function. In other words, thermal control or attitude control. And the problem is we don't have a rational architecture that connects these two things, particularly for large space systems. So my point is, you're trying to manage something, you don't even have an aspect where you can measure what you're doing. And so this is the big hole I see in big programs like Artemis and probably a lot of other things that go on in the high-tech world. NASA has got to take a role in basically laying down the standard for how these physical and functional things interact. And then we can decide what part of that domain the humans own, what machines own, and what they have to do collaboratively. And so we have got a lot of homework in front of us, but we haven't even recognized that this is a problem. So let me leave it. I've got a lot more to say about autonomy, but we've got a lot of time today. So let me leave it there for my comments. And maybe if you want to quiz me on what I said, that'd be great, because this is a very deep topic.
Great, good kickoff there. And one of the things I think is always appropriate is when somebody says what they think autonomy is to question that, because it does mean different things to different people, and in the differences of meaning hides threat and risk and unknowns. And one of the unknowns you bring up is the explainability of what AI can bring to us, because AI systems, machine learning especially, convolutional neural nets, the guts and heart of a lot of AI systems, are not set up by logical processes like we are. And fortunately, we have somebody who's here today, Tamer Barkouki, who, besides his operational experience as a Air Force PJ, is developing the principles for explainability for AI-driven robotics on spacecraft that work with human beings. So we will get to Tamer, and so it's fair warning to Tamer to kind of address Shep's question. And what I expect here today is not answers to these questions, but expansions to add wisdom to these questions, to help us guide where to go, help NASA, help universities, help the commercial companies guide where to go from here. So let's leave these questions that Shep has brought open and on the table, and for the moment, move forward. Our next panel member is Dr. Allie Anderson, who's a colleague, an old friend. We collaborate on several kinds of research. She is a professor of aerospace engineering sciences at University of Colorado. Her work supports humans doing exceptional efforts in demanding environments, such as in space, and their research includes EVA, various types of alternative reality information technologies, and also SANS, neuroocular syndrome, which has been a big topic in this summit, and also human resilience, and the isolated, confined, and extreme environments that we're talking about here. And Allie, I have a question for you too, specifically for a deep space long duration habitat. How should we address an astronaut's ability to accomplish a human autonomous robotic system teaming task, especially when it's prior to some safety critical operation? So what aspects do we need to assess? How might astronaut crews learn to trust autonomous systems? Kind of a big ball of questions there for you here, Allie. Nobody better than you to answer.
I don't know about that. I think all of your questions are very big. So, but first I wanted to say thank you so much for having me. I'm really excited to be here. Thanks to those of you who've organized the summit, Mr. Abbey, everyone at the Baker Institute, and of course, all of the incredible panelists we have. So I tried to break your question down into a little bit more manageable chunks. So the first part of the question was really, how do we assess people's ability to perform these kinds of tasks? And I think the emphasis on safety criticality is an important one. And these are tough challenges that many folks are working on, whether that's at NASA or in the research domain, looking at things like fitness of duty standards or monitoring performance, using sleep aids to facilitate better performance and restoration. And I think one of the primary dimensions that makes this hard is that we're dealing with individuals, and making an assessment on an individual is not making an assessment based on the average of our data. And that degree of personalization makes it very difficult to create sort of standards around some of these challenges for how do we know when someone is ready to perform these tasks. So, I will echo a comment that you made earlier, which is that, also in my personal opinion, I believe that for any human autonomy teaming task, we have to trust our crew members and believe that they will be the most capable to make decisions. I think this is particularly true for decision authority, task execution, and monitoring of system states. I think that should absolutely leverage autonomous systems, but the actual decision-making authority, humans are so good at making decisions in novel situations, and for these LDEM type missions, that's exactly what we're going to be dealing with, or novel situations. So I think taking what we know about how good humans are in those situations and making sure that they always have access to that decision authority. One of the other dimensions of your question was, how do we actually go about assessing it? And I think there are different strategies that should be used depending upon the kind of autonomous system that we're really talking about here. So in some of the groups that Steve and Tamara and I collaborate on, we talk a lot about the difference between embodied autonomous systems. So embodied systems being like robots versus embedded autonomous systems, say like working with algorithms, and how we actually use different types of strategies in these either human in the loop or human on the loop settings. We also focus on looking at specific cognitive constructs that are known to be really important for human factors and human autonomy teaming. So specifically looking at trust, workload, and situation awareness. But at the end of the day, what you really care about is their performance and their ability to actually execute the task and to execute it successfully. You focus specifically on the state of trust, and the question is, how do we make sure that humans are able to learn to trust autonomous systems? And I think there is a whole can of worms that can be opened here. And I know actually, I think both professors Aquila and Stankovic might touch on this as well. Actually, I think we'll probably all touch on this a little bit. But you know, I take the philosophy that humans must establish trust with autonomous systems in the same way that humans establish trust with other humans, which is through repeated exposure, repeated interactions that allow the person to really understand the limits and the capabilities of the autonomous system with which they are engaging. And I think that one of the challenges is giving someone an opportunity to really interact with autonomous system when it might be acting for the first time, say, on that planetary landing task, you know. And so ultimately, in my opinion, it comes down to actually training with the environment to the best way that you possibly can, both here on Earth as well as in preparation or in transit. And then I'll also augment that by also saying, I think, especially for autonomous systems, it also comes with a healthy dose of skepticism in the same way human machine teaming is done. So, you know, I think a classic example there is, you know, a pilot with an aircraft. They trust the mechanical system of the airplane, but they always inspect it prior to their flight. And they also have developed a deep understanding of how that mechanical system works. So long story short, I think one of the best ways to really ensure and assess that the human is able to interact in these mission critical tasks after a long period of time between Earth-based training and the actual subsequent action that they're going to be taking collaboratively with the autonomous system is to give them the opportunity to interact with and practice, and to use that as an opportunity to also assess performance. So that's my attempt at taking a chunk out of your big question.
Thanks a lot, Ellie. I think the topic you bring up of decision authority, always coming back to the humans, I think is something we agree on a lot. And it brings up the idea of, you know, you hear like Alonso Vera, NASA Ames talking about intelligent assistance a lot, and a lot of other people in the field. How do we provide tools for humans to make the best possible decisions, especially when they're fairly new to the spaceflight environment? If you've been in space for a year or two, your capability of making the best possible decision in a short amount of time and the safety pressure might be different than in your first week. And somebody, you know, very often we're going to have people in their first week or month in space. And so I think helping humans be the best, the wisest, and the most correct authority to make these decisions is something that is a research topic that goes right along with this human autonomy teaming. So thank you for bringing that up. All right, next we have my friend and research colleague, Dr. Sandra Stankovic, who is the director of the Human Performance Lab at Harvard Medical School and Mass General Hospital. Her research includes high-level human performance and behavioral health for individuals and teams in extreme and isolated working environments, particularly spaceflight, through optimization of crew selection, training, teaming, and cooperation between humans and robotic and autonomous agents. Exactly what we're talking about, and that's why you're here, Sandra. My question to you is, how should onboard autonomous systems communicate with the crew? So by communication, I mean, if you think about task execution, prior to task execution, the autonomous systems and the humans need to come to some sort of understanding. Kind of communication does that require? During the task execution, how should the human monitor or help? And afterwards, how can you assess the effectiveness of the task that was accomplished? And maybe you could also address, should these communications approaches and interfaces, should they be adaptive, customizable to individual crew members, or is that something that should be not be the case and should be covered through crew training and experience? So another big ball of questions for you, Dr. Stankovic. Take it away.
Thanks so much for that question, that set of questions. And thanks again to you and to Mr. Abbey and all the organizers of the Baker Institute for having me on this great panel. I'm thrilled to be here and get the chance to learn from all of these amazing panelists. So I think your question really gets at the heart of some of the biggest design challenges for enabling effective human automation teaming. Interagent collaboration really hinges on, like we've talked about already, cultivating trust through very clear explainability on the part of the automation. And humans need to understand, what is the automation doing and why? How did it come to its conclusions? What does it plan to do? What is it actually doing? And then what really happened once the automation has executed? And promoting this kind of transparency becomes really complicated because, as you've already mentioned, Steve, AI systems, they're not replicas of the human brain. They don't think like we do. They don't assess risk and make decisions and communicate like humans. So following their thought process can be extremely difficult for a human operator to understand. And that's where this optimal communication piece comes in. So that, information presentation, it's a really big challenge. And I think you can start to break this down into maybe 3 subcategories of questions, the sort of the what, the when, and the how of presenting information. So, for the what, it's really a question of what is the right information and what is even the right granularity of information to present to the human. What does the human really need to know at any given moment about both the state of the system and also about the automation and its intentions? And how does that question maybe interact with task and with time? So, these aren't really static things we'll be looking at. There's changes that will need to be accounted for. So, cognitive load or the burden on the operator, that's going to vary across not just the mission, but across any given activity as well. And the how piece, I think, is equally crucial. What are the right channels and modalities for communication? What's the right bandwidth? How can this information change and adapt and be customized for humans and maybe configured based on their own needs and in response to dynamic situations? Or when unexpected contingencies occur. Professor Anderson just mentioned that, and that's such a great point that we'll be facing a lot more of these types of unanticipated problems and failure modes as we move beyond low Earth orbit. And this question about how the automation is communicating, we can open up a whole new set of channels, haptic channels, different ways of presenting information when maybe, let's say, your visual channel is already overloaded by a task. So perhaps that's not the best mode of communication at that time. So having some dynamic component even to the way that the information is being presented could be really novel and innovative and impactful. And then this customization piece, Steve, that you brought up, maybe that needs to be built in as a design requirement. It's something that can account for changes in the level of information need that an operator might have at different points of an activity. So, I could imagine something like preset granularities that the human would select, and those could shift at predetermined moments of transition during a task or an activity. So, imagining something like a really sophisticated version of the declutter levels that the space shuttle display had. So a dynamic interface that could present these different levels of information density that the human can control based on what suits their needs in any specific context, or based on the workload that they have, and even based on things like proficiency and experience. And as you pointed out, Steve, we're going to be dealing with crew members of different kinds of experience levels as well, and so you need that robustness built into the communication modes also. And ultimately, I think the crew is going to need to have a central role in defining how these interfaces are designed, how they're customized, tailoring them. What you really want is kind of like an optimal value to nuisance ratio, because if that's poorly calibrated, the automation can end up creating more confusion and cognitive burden on the human rather than supporting them. And that would really be an unfortunate situation. So those in my mind are the biggest kind of open-ended big ticket questions. I know I've asked you more questions back than I've probably answered, but I think we'll be seeing a lot of really interesting work in this space in the coming few years. So I'm excited about that, and I'm looking forward to hearing the thoughts of the other panelists.
Thank you, Sandra. I think where we are right now in integrating humans with semi-autonomous systems in spacecraft is just what you said, trying to figure out what are the right questions to ask. None of these questions can be solved by what I call opinion engineering. There has to be research, scientific method approach, and bringing in the deep experience of people who've flown spacecraft and thought about this for many years, such as Shep and Wax. I like your value to nuisance ratio. Crew members try to optimize that themselves, especially when they're new. I remember that. And when you talk about information presentation to a crew member, it struck me. I remember when I worked in mission control for many years as a Capcom, and I remember learning how to do that, thinking, I don't think I'm ever going to get all of this information that's available to me in front of me on all these screens into my head at one time. And eventually you do, but it definitely took a long time. But in contrast, if you've ever been in the cockpit of a modern airliner today, it's amazing how little information is actually displayed. Now, the crew can call up whatever information they want about the systems, but for normal operations, there is very little information displayed. Just the raw flying information that you need, and that there is partially the difference between a highly evolved and reliable system in the airliner, in which things go wrong quite rarely nowadays, and a spacecraft, in which is largely assembled with serial number 1 and 2 things, subsystems, which lead to all kinds of degradations, faults, surprises. And so the amount of information that you need to have available to you is quite different. Okay, thank you for those insights. Let us move now to Tamara Barkuki, who is a U.S. Air Force Reserve Special Warfare Pararescue, or in other words, PJ specialist. He's also a UC Davis PhD candidate in the Center for Spaceflight Research, and he's the chief scientist in that operation. Tamara's research includes AI explainability for human-robotic collaboration in spaceflight. So this is what we brought up right in the beginning. And my question to you, Tamara, is since machine learning technology does not generally use logical inferences as humans do, how will onboard and distant humans understand what autonomous systems are doing, what they recommend, or what it does, especially for safety critical operations? Like I say, what isn't safety critical when you're in space? And what constitutes, when we're talking about humans understanding what AI systems are doing, what do we mean by that? What constitutes sufficient understanding? So over to you, Tamer. Good luck.
Thank you, Professor. Thank you for the invitation to be on this distinguished panel. I'm honored. So your question on how to understand data-driven autonomy is the objective of the field of explainable AI, which is the concept that's been around for decades, really since the beginning of AI research, but has picked up steam recently with DARPA's explainable AI program to answer these questions for the DoD, and has since spilled over to almost every application of AI. And the problem comes from this trend that the higher performing algorithms being developed today are impossibly complex to understand, even by their developers. And in some cases, they're subject to unpredictable or catastrophic failure when they're fed data that's outside of their training set. There are emerging methods to help the developers better understand their models, to develop surrogate, simpler models that they can use to kind of poke around and understand what the model has in its internals and debug them. But for the operators, for crews and flight controllers, we need different tools. We can't just give them a simpler model to look at. We need real-time capabilities. So for that, the explainable AI field is starting to look more into the behavioral sciences to understand what makes good explanations, what makes explanations satisfying to people. For example, a question that we hear often when people say something is why. You know, why is that the case? Why those things? Really, what we're asking is why not something else that I might expect, right? You're asking why not something that I anticipated when you ask a why question. And that's kind of analogous to, in the medical field, a differential diagnosis, right? You rule out diseases or conditions based on the data you have to arrive at the correct one. So imagine you have an AI analyzing time series sensor data for a subsystem in the station, and it's experiencing an anomaly, and you want to know why, right? Well, you don't want just the root cause, but you also want kind of succinct reasons about why there's a low probability of there being other causes that the AI is providing. There are methods for that, but they're not exactly off the shelf ready right now. They're computationally challenging. So depending on the application of machine learning, you may have the need for high-end computing and some time to provide an inference. And now you're asking it to search over a space of hypothetical outcomes and explain why those aren't the case and why the input to the model is different in those cases than the true nature. So that problem is generally not solvable, at least not quickly, even with specialized hardware. So the present solutions right now are to have a human expert provide domain-specific knowledge to constrain the search space. You have machine learning plus domain experts kind of sculpting these explanations. Those may work for constrained cases, but for general usage, that's not ready yet. Again, the analogy to the medical field is diagnoses tend to be grouped by similar patient presentations. So you may have a sort of a checklist of for anything the model spits out, here's why it's not something else related to that. Your second question about sufficient understanding, I think we have to look to the human factors field for the metrics that we would use to say that these are understandable. We have a body of literature on causes and consequences of mode confusion and loss of situational awareness in increasingly automated cockpits. And now that's starting to creep into autonomous self-driving cars. So we can look to those and say, what does the human need to know about these systems? And I think it's simply what they need to know in order to perform their roles optimally. In this case, for an embodied robot, like we've heard, different types of AI, ones that are more data analysis, ones that can actually act on the world. We need to know not only their current state, but what they may do in the future, in the near future. So that's what you need for the crew member or for the flight controller to do their role optimally. You need to know how to recognize when the system is failing or when it's out of its element, when the data it's being fed isn't part of its training set or it's out of distribution. And lastly, you need to know how to regain control in the autonomous system. So we heard you mention that humans always need to be able to take over. But if the system is sufficiently complex, just having the ability to take over may not be enough, but how to take over. What was the current state and the near future state of the system when I take over to have full SA to be able to regain control properly. So I would argue you need at least those three to have sufficient understanding for safety critical setting. And I'm excited to hear some questions.
Do you think that sufficient understanding really depends on each individual human? If you're explaining something to me that is complicated, at some point I'm going to say, yeah, I got it. That brings up a couple of interesting things. Could you have predicted, somehow set up a system that would predict when I would say, yeah, I got it? And after I say, yeah, I got it, how do you know I really do? How do I know I really do? Confident people tend to say, yeah, this is like something I've seen before. In my experience, yeah, got it. And it could be completely wrong. And I know I can come up with examples in my own life where in my life as an astronaut, where I would prematurely thought I understood. As you rightly say, this is in the realm of human psychology. So maybe all of us have to think about when we're talking about explainability and sufficiency of explainability. It's okay to over-explain maybe, but it's never okay to under-explain. Want to address any of that, Tamer?
I was hoping that was a rhetorical question.
So yeah.
There are some efforts, right? And we've heard from Dr. Stankovic and Dr. Anderson measuring trust in real time using different forms of interaction, right? The way humans do. If you ask me why and we don't know each other, I may give a generic answer based on what I know about you or your disposition, right? Your education or maybe even what you're wearing, right? It's not something that's very human in that sense. But as you ask questions and as you respond to that, I then shift, right? It may be very simple at first, see if that's satisfying, and then we go down a rabbit hole of questions and answers. So I wouldn't say that those are available, but there are directions to start based on understanding of human reactions to information, and using psychological measures or physiological measures to see if they're satisfied with the information they're getting.
Dave, can I throw a small wrench in the discussion here?
Throw away. I'm counting on you for that.
We talked about the commercial cockpit, and The gate people open the gate, people walk down the jetway. The captain sits in the left seat, the co-pilot sits in the right seat. Those two have never flown with each other, but somehow they have trust. How does that work? It's probably a question for later, but before we get too excited about airlines are great, we have to understand that.
That is an interesting topic. I could say a lot about that too. Let's keep that that particular can of sardines open on the table here, Shep. And thank you, Tamer. Lots more to say and talk about, but let's move on to Dr. Katja Arkia. Katja is an assistant professor of aeronautics and astronautics at MIT, and she's working in the lab that Ali and I and Sandra have been associated with in the past. Katja's research includes quantifying human state to improve psychological health and task performance in challenging operational environments, exactly what we're talking about here. And my question to you, Katja, if we can learn to assess an onboard astronaut's physical and psychological state in real time, and that's a huge if, of course, what do we do with that information? Should there be some kind of standards to measure these against? Well, there are for physical, but for psychological, people, we've all been researching and behavioral health and performance within the NASA HRP, been working on this for decades. But how do we apply these standards in long duration deep space operations on board, like we do now with MCC and Flight Med, or in some sort of partnership that is different than what has been done so far? What is your thoughts on this?
Yeah, great question. Thanks so much for having me as part of this panel to kind of ground this question in some of what we've been talking about in the issues around explainability and leaving decision authority to the human. It's really important that we're able to characterize the state of the human. And we've actually seen experimentally that operators kind of governing strategies around their use of automated or autonomous systems are highly variable depending on their psychological state, their physiological state, their social interactions that day. And so this kind of drives the need for being able to monitor people in this way so that we can better design autonomous and automated systems so that people use them appropriately, because we often see that people are not using things the way that we intend them to. So to the question of standards of measurement, in my opinion, ideally, these standards should be based on each astronaut's baseline state in different environments. The issue with having a single standard that you're comparing everyone against is that it limits our view of health and performance and reduces eventually the diversity of the crews that we send. And we've seen this historically in human spaceflight, where if you're comparing everyone to a standard that's set by the majority of the population, you're going to miss the nuances that people can still be high performing and highly capable, but just have a different flavor to their standards of measurement. The challenge with this, of course, is that characterizing someone's baseline is incredibly difficult. You probably all know that some days you wake up feeling better than others, and doing that type of characterization really requires extensive longitudinal data from each person. And the question around when do you take that longitudinal data? How much do you need from the ground? How much do you need in microgravity if you're using something like a wearable sensor system? We really don't know the answers to those questions yet, and how to actually characterize an individual in an operational environment. To your point of what to do with the information once you've collected it, hopefully. In my view, it's important to empower the human to make their own health decisions and have some governance and agency around how their data is used. And I think that just this level of kind of crew autonomy, of having power of their own data and monitoring capabilities, can provide in and of itself a behavioral health and performance support tool. You can see this with wearable systems on the commercial markets right now. People love to have an understanding of their own physiological health, and just providing people the control to make their own decisions is very helpful. So I see in future long duration missions kind of moving away from the checking in with ground control so frequently, and really encouraging crews to help monitor themselves and monitor each other. And then, along the last part of your question, I think the really important capability that this drives, this real-time assessment of physical and psychological state, is that this can actually be fed into automated systems that astronauts interact with. This would potentially increase explainability and also activates the operator as not just a passive operator, but also an active agent in the human autonomy team, which I think a lot of work in human robot interaction and human computer interaction kind of treats the human as a passive system, or models the human with, choose your favorite statistical approach, and doesn't often actually take information from the human and give them agency to make change within that team. So I think that's a really important reason to have real-time monitoring on long duration missions. But of course, the huge challenge here is data management. We'll have fewer computational resources in deep space. And so algorithms that are developed for real-time detection have to be really lean, which most of what we're doing on Earth in this space is not lean and is computationally very heavy. So that'll be a challenge to address in the future. And I'll leave it there for now. Thank you.
Thank you. I was hoping somebody would bring up the concept of agency, or as you put it so well, as activation of the human as a very important collaborator in the human machine teaming. You would think that would be sort of obvious and going in, but as you say, it sometimes is not, where the human is thought of or designed more as an operator to do the right thing. And so this sort of sense of agency that you have deep understanding and can adjust to just about everything that's going on. I think basically every astronaut would agree that that's an essential part of successful spaceflight. Does this mean that astronauts and mission controllers need to be trained to optimize this idea of agency in a crew autonomous situation in deep space, where you just don't have that second access of MCC? In other words, I guess I'm asking, how do we improve this sense of agency on these type of flights with these squishy humans involved?
Yeah, I can take a first stab at that and then invite anyone else who wants to comment. I think the type of crew member we're sending on future long duration missions is fundamentally changing from the crew members we used to send and routinely send to the ISS. This requires different training protocols where, maybe we do training with less feedback, or, structure decision support really differently than we have in the past, and develop decision support tools that are able to autonomously update depending on environmental conditions or spacecraft conditions. So I think we will fundamentally need to change the way that we train crews and potentially the way that we select crews for future missions.
Okay, that's a huge topic. About what should future crews actually know, since the concept of spacecraft is actually changing if we're going to have embedded autonomous subsystems. Okay, that's another one to leave on the table. I'm very pleased to welcome to the panel here Captain Jim Weatherby, who, besides being one of the world's most accomplished rock and roll drummers, has done other things in his life too. He's a retired U.S. naval officer and naval aviator. test pilot, aerospace engineer, and very accomplished NASA astronaut, a veteran of 6 space shuttle missions, and the only American to have commanded 5 spaceflight missions. Welcome, Wax.
Thank you very much for having me. It was great to see that you're moderating the panel again, and nice to see the rest of the team.
Well, I have a question for you, and you're a little bit in catch-up mode here. I know that, but I also know from experience that you're very good at doing that. So my question is, how should we develop and validate the design principles for integrating autonomous systems? And Wex brought this up right at the very beginning of, rational architecture for incorporating autonomous systems. And he did it in the context of, are they deterministic? In other words, do they give the same answers for the same inputs each time? What about explainability? We've been talking about explainability of autonomous systems to humans quite a bit here. So how do we assess in real time and ongoing, how do we assess the strengths and weaknesses of the humans and the autonomous systems? And then maybe lastly, I'll ask you to dive into that idea of how do we train to successfully team humans with autonomous systems for spacecraft?
Yeah, so great question. Thank you very much. So I've been thinking about this for the past couple of days as we get ready for this symposium. How should we develop and validate the design principles? I think, so this is the 3rd year that we've gotten together, and I've really appreciated the opportunity to talk to the group. And I have a list of principles that I wrote several years ago, and I have been modifying. I think it's time, Steve, that we conduct a workshop sometime in the following year. At such a workshop, I think we should invite product owners. So that would be the astronauts, flight controllers, surgeons, and a group of subject matter experts. That would be designers, coders, engineers, testers, system safety folks. Very critically important to invite some UX, UI experts, user experience, user interface people that understand human factors. I would invite psychologists, academic researchers, such as the people on this team, and I would include ethicists, if that's a term, because as you know, ethics is going to be a big part of autonomous systems. Once we convene a workshop, the very first thing I would do would be to propose and brainstorm a list of principles. You can start with the list I have or start with any list that you want. And just develop a list of principles that should be followed. I still think, as I work with industry and the government in the past, I think it's coming that we're going to have autonomous systems, certainly in the weapon system. I know that's not the purview of this conversation. We're talking about spaceflight, but it's coming very fast where systems are being designed in the weapons area. And I don't think we have really written down or codified the principles for autonomous systems and how we want them to operate. Once we decide a list of or codify a list of principles, I would do the following things: compile a list of the strengths and weaknesses for both systems and humans, and I've added a few since last year. In talking with UX, UI experts. And then how do we assess those strengths and weaknesses of the systems and the humans? And that would be through testing. So one of the first things you do is codify a model of how human operators think and work, include the differences in humans, because we're going to have different individual humans on board, including the skill level, and that can sometimes change depending upon the environment or the mission. Include the environmental differences. We're working in microgravity. There's fatigue, voice changes, vision degradation, stress, those kinds of things. Next, codify a model of how the systems will be learning in the future, as we have autonomous systems that probably will be learning on their own. and then codify a model of how we want the systems and the humans to work together, including, and the thing that's new for me, I've always known that we want the systems to be able to help the human, but we have to do the reverse. How are the humans going to help the system to learn? How do we assess the performance of each, both the system and the human, and how they're working together? And how do we modify the performance for specific users? Do we have an autonomous system that operates differently when it's working with a different human being? Next would be on the agenda, develop a testing matrix for how we're going to test all these assumptions and models that we're creating. So you start with writing down a list of assumptions. What do you want to test and validate? In the banking industry, they're creating applications with automated systems, and the first thing they do is to test what they call the happy path or the heart of the envelope. So then you want to test the edge cases, degradation testing. What happens when the system starts to degrade or have certain mode shifts? How does the system operate? How does the system self-assess its own performance? And we need to test those kinds of operations in the system. Develop and write down a matrix for criteria for success and failure and test termination. How do we remove biases from the testing? What is really affecting the outcome of the testing or the performance of the system? How do we anticipate and identify unpredictable outcomes with systems that we're designing that are getting incredibly complicated? What are the ethical implications of the testing? Certainly it should be voluntary testing. What happens to the results? Do we share the data? Those kinds of things, all kinds of ethics questions that we have to develop and write down in such a workshop. How do we verify the state of the system if it's actively learning? How do we really test and know that what state the system is in? How do we assess the results and how the system is affecting other systems that it may be integrated with? We need to conduct empathy interviews to know how the humans are operating with the system, and conduct heuristic evaluations of the test results. That's what I would do in a workshop to develop the principles and the design inputs that we want. Once we start developing and validate or developing a system, then we have to really start to test the system using what I've just outlined above. And then you also talked about, I'm almost to the end of what I wanted to say, how do we train the humans and the AI? Considerations that we have to think about are, number one, it's not going to be like when you and I were astronauts, Steve, and we really could understand down to the ones and zeros level of the software and the system and how it was operating. We're not going to have that luxury in the future. The system is going to be so complicated that we won't really understand down to the basic ones and zeros level. But we do have to understand various things, how the system is performing. What is the mode or the state of the system? How do we intervene as human operators? How do we safe the system if we think it's getting out of parameters? How do we return control back to the system if we've already intervened? How do we operate when the human is stressed? The classic example of these new systems, a major pizza company designed an app, and they were testing it and rolling it out, and users were using it. And then they realized a little bit too late that the majority of the people who were using the app were inebriated when they used the app, because that's why they wanted the pizza. So they had to design the system to be used by people who were not at their full potential. Regarding training in the system, I had a conversation recently with somebody who's working in Space Command, and he was saying that the young people, they don't want a user's manual. like you and I did when we first joined the program. And I'll give you the user manual and I'll dig in and figure out how the system is working. The people these days learn training from either the system is similar to one they've already seen before, so you have standardization. Classic example there was we used to have to read a checklist on how to connect Bluetooth. Well, these days everybody understands the symbology because it's standardized, and I can connect various different systems together because I understand how that works. The systems in the future will have gamification. You can, input the training into the system itself. So as I start to use the system, it trains me how to use the system. And then I'll just close and say, if we don't jump on this now, we will be behind. We also can jump on it quickly, conduct such a workshop, and then maybe help the other industries. One of the great things about NASA is we can have spin-offs that can help other industries, because these weapon systems are coming. MIL Standard 882 Rev F is in draft now, System Safety Handbook. And it doesn't even include autonomous weapon system safety. And yet we're starting to ask companies to design weapon systems that are going to make the decision on what target and who to kill without the human in the loop. And so we really need to be jumping on this quickly. Of course, the great benefit is we're going to help spaceflight travelers into the future, because these systems are going to be not only necessary, but desired and important and all that. So thanks for having me.
Thank you, Wex. All that clear thinking is exactly why you're here. And this is the third time we've had this panel, and we're building on our own knowledge as we go forward. We're only going to have Shep here for another few minutes, and so we'll get back to some of the interesting questions that you brought up, Wex. But at this point, let's go back to Shep. You've heard us all give a slight overview of our view of the corner of the world. What are your thoughts now, Shep?
I really like Jim's idea of a workshop. I'd like to suggest that somehow somebody in the government sponsor this, so it's kind of a neutral event, and we invite people from all over the tech industry to come and show, basically roll out their trading blanket and show us some of what they're developing, because I think this is all, the technology is moving so fast, and that's the only way we're going to at least even be aware of what is coming in the way of machine interfaces and things like that. So that should be a big part of the workshop, I think. The other thing I'd like to say is, can anybody say for the human machine interfaces, what kind of language should the computer talk to the human in? Can anybody?
You mean English versus Russian versus?
Yeah, we want to use
English?
English?
Graphical versus?
Well, I'm going to get to that, but should we use English?
Should we use the language that each user is most comfortable with?
Well, I'm getting to the point. We have a convention, whether we know it or not, that the more important things on a page are in the upper left, and the lesser things are on the lower right. And we like stuff in English. And we like that our switches, when they're in the up position, something's on, and when they're down, something is off. And there's a large part of the world that does not work this way. And so we've got to be very careful when we create, if you will, standards. I think, as an example, text-based systems for communicating with humans are generally a bad way to do things. And the HUD's a perfect example. I think pilots get a lot more out of the heads-up display because they're looking at the circles and the dots and the diamonds than they are what the text is saying, whatever else is going on. So I just caution that we go too far down the road too quickly, saying everything's got to look the way that we like it, because I'm not sure that that's optimum, even for us. So
it was
good. I got to wrap it up here.
I know you do. I really enjoyed training in Russia because some of the user interfaces were so different than anything that I was used to. And rather quickly, I became, I preferred some of them. There were new and different ideas, and it just spoke to me in a different way. Before you go, Shep, almost the first thing you brought up was whether the challenge of humans understanding what autonomous systems are actually doing or want to do, this idea of explainability. So several of us, especially Tamara, have addressed this. Before you go, as your wrap up, give us your thoughts and cautions about how we should address this.
Well, one of the things that I think astronauts kind of gradually get accustomed to, some of us take more time. Captain Weatherby was really good at this, but when you get ready to do a procedure and you got your finger on a switch in a spacecraft, the varsity astronauts are thinking, what do I expect to see happen after I flip this switch? And if that's not what's happening, then what else is going on? And so I think that's tied to this whole explainability thing. The culture of, I think, astronauts and pilots, this is the way these people are trained, and that's how they think. And if we cannot dissect what the autonomous system is doing in the same fashion, I think it's going to be a different world.
Tamara, would you like to respond to that as the resident expert of explainable AI?
Yeah, sure. I think that's the issue with the autonomous systems that are trained on machine learning, is that you can't fully know what to expect when you flip that switch, and that's why I brought in examples from the medical field, because I'm trained as a medic, but I think any provider learns that there's no switch on the human body, right? You try things, you look at the outcomes, and then you kind of put that into a category of what you expect and what you don't expect to drive how you try new things. So I think you have to kind of take from other fields besides conventional aviation to look at, here are the classes of things I expect, and here's what I basically having backups ready to go when things are when other outcomes appear, right? So I think approaching, and at least initially, with some skepticism, any machine learning or data driven, or even if it's logically based, like Captain Shepard said earlier, higher levels of layers of complexity, even if they're not data driven, but they're just very deeply stacked levels of technology, have non-deterministic outcomes, at least to the user. Having readily available procedures for addressing different outcomes or different classes of outcomes, I think is the first way to go.
Steve, let me throw one more thought on here. Real quickly, back to the function and what are critical functions and things like that. On our last flight on the space station, we had some instances where, I wouldn't say the crew was arguing, but we were at odds with what everybody thought should be done. And I said, okay, look, we're here to do this, this, and this. And at the top of the list is making sure that the spacecraft doesn't get dinged or something really adverse happens. These other things they're not on that level. So we've got to do this right now. We can do this other thing 20 minutes from now. But without that structure, you're not going to have, and the structure evolves. It's changing by time and where you are and what you're doing. That's what's got to be mapped out, and that's what's missing. So that's my drum. I beat it every year, but maybe you guys can make sense out of it. I really like the workshop idea. Just tell me when we're going to have it. And I've got to sign off.
I know you do. Shep, thanks so much. Keep beating that drum. We are listening.
Okay.
I think we are learning and getting better. And the next you're going to hear from me is to form a organizing committee for a workshop. Professor Allie Anderson had to go off and teach here. Here's what I'd like to do: is I'd like to go back to my other panel members, Dr. Kia and Stankovic. You may have burning things that you've developed in your mind that you'd like to say, and then I'd like to go to our audience, if that's okay with you, Richard. Yeah, Richard says yes. Okay, gotcha.
Yeah, a lot of ideas formulating from this conversation. I agree that it would be great to have a workshop and kind of hammer out more of the details. I think we've talked a lot, generally about the existing problems and the growing problems, and it would be fantastic to just sit down and go line by line and think about, okay, what's the actual research we need to do to get these problems figured out? So that's on my mind at the moment. I'll pass it to Sandra.
Thanks for that. And sign me up for the workshop too. Sounds like a great idea. I wanted to pick up on a theme I think that's emerged from this conversation. For me, seems to be a kind of an implicit tension between training and improvisation. We've talked a lot about, what you can expect from the automation, how you can train your crew members to be proficient and deeply understand what the automation is doing so they can collaborate more effectively. But something that I think has come up in the comments from the other panelists, and you see this a lot in the human factors field, is that, either your operators aren't using the system the way you anticipated that they would use it, or that they're, something about their current state or the situations in which they go to the automation is not the same as you would have initially expected in the design process. And we've already mentioned a couple of times how, as we move beyond low Earth orbit, we're going to be encountering a whole different set of problems of, types of operations that won't be as choreographed. We won't have as deep and wide of an understanding of all of the possible contingencies that might arise. So maybe we're moving away from a model of training for an activity, but instead training crew members to solve problems more effectively. And that will involve being able to be dexterous in the way that you work with the automation and the way that you leverage it in certain kinds of situations. And I think this goes back to something Katya mentioned earlier about, really empowering the human and activating the human in the teaming relationship. And, that's something that's interesting and exciting for me. So I'm glad we picked up on that.
I think that concept of being intellectually dexterous is what keeps you alive in space. It gets back to some ways to the old differentiation between skills training and task training. There's no way you can be fully task trained. And the question is, can you be fully skills trained? And now we add to that, when we're talking about human capability, we add to that these intelligent autonomous systems. Not intelligent at all, they're autonomous systems. But they try to make the human more intellectually capable, or more intellectually dexterous. I want to circle back to Wex before we jump over to audience participation here. Wex, tell us maybe the top 3 of the principles on your list.
So thanks. And I've broken it into 2 major categories. The first category is the principles of the automated system itself. And then the second category is the principles of human oversight and interaction with the system. So in the systems alone section, the system should always have the ability to perform autonomous self-assessment. So it's always got to be looking at its own performance and enunciating the health of itself to the human. It should, leads into the second principle, enunciate self-assessment results. The third principle is it should be self-limiting. In other words, it should have graceful degradation and perform self-modification if it starts to sense that it is lacking in certain inputs that it needs or its own performance is degrading. It has to be able to mode switch or go to a fail-safe or fail operational state. The fourth principle is it needs to afford intervention by a human. And then the fifth is to be able to accept control after a human intervenes when the human decides to give control back to the system. The new principles that I haven't created that we need to are in the area of ethics and learning. What are the principles of a system? How should it learn? How should it modify itself? Does it write new software as it sort of evolves. And then the section on human oversight, the humans must always expect failures and degraded performance of the automated system. Secondly, the human must be able to evaluate the performance of the automated system. Third, be able to intervene or override automatic or automated operations. Fourth, know when intervention is appropriate. Fifth, know how to intervene. Sixth, be able to communicate the current state to the autonomous system. How do I tell the system once I've taken control and maybe it stops receiving inputs, how do I give inputs back to the system so that it can gracefully pick up and conducting its autonomous operations? And obviously the human has to know when and how to return control to the automated system. I think that's it on the principles. That's certainly the top level.
Good. That gives a flavor here of your thinking. And let me just say, I really like the idea of a workshop to collect people's ideas. Again, I think where we are is defining the questions that need to be addressed through research and testing, not so much answer-driven workshop. But this is a field that has generated a lot of opinion in the absence of a lot of experience, and so it's certainly the right time to be doing it. Richard, how shall we bring in questions from the audience?
Well, they have a question and answer box. I haven't seen any questions there in that box. You can ask them. We're probably getting to the time to terminate also.
I think we are, but we have a very distinguished set of attendees and participants and lots of friends. And I encourage you to, in fact, I'm a professor, I can do this. John Clark, I'm going to call on you because I know you have thoughts about this. So would you be so kind as to type in your burning idea, thought, or question into the Q&A box, John? While we wait for John to deliver on his assignment, and he could be off getting coffee. I will also ask the same of Bob Thirsk, Canadian astronaut with a lot of experience in technology development, and I'm sure you've been thinking about incorporation of autonomy. So Bob, thanks for coming here today, and jump in with a question in the Q&A box if you want. And if I haven't called on you, that doesn't mean you're not welcome. Please do, in our last few minutes here, type in your question in the Q&A box. While we wait for other inputs from the crowd here, how shall we do a workshop? Well, the workshop's going to need a little bit of sponsorship for people to travel. I think an in-person workshop is a lot better than a virtual workshop. Just being face-to-face, you just can't beat it when you're talking about difficult topics like this. And so I think sponsorship is going to be a challenge for something like this. And I think what I would like from each of you on this whole call is, if you want to be involved in a workshop of the sort that Captain Weatherby has come up with this idea, then please let us know. Let us know in the chat, send me an email, send anyone an email, and that'll get to me. And we will start kind of stirring the pot. Hello, John Clark. I want to talk about your thoughts about the challenges of incorporating semi-autonomous systems with humans in spacecraft. In other words, systems that are doing things on their own, that the humans may or may not be currently engaged in, but can affect their health and safety. You can just type that in the chat. And I think we're probably going to run out of time here. We're at 11:45. We're getting up to lunchtime, I believe. Is that right, Richard?
Yes, that's correct. Yeah.
Okay. Okay. Well, I'll go ahead and take John's thoughts offline. Please contact me through the Baker Institute, or Richard, if you want to be involved in this and thinking about how this workshop.
I think Stephen froze up. I think we probably ought to go ahead and finish the panel now, since Steve is offline. I'd like to thank all the participants from this panel. And it's been a fantastic panel. It goes in, now Steve's back, it goes in very well with the one we did earlier, looking at time delay on the way to Mars and how best to handle that. One thing I will mention, and something that Steve also just mentioned, the panel's in today for 2022, but the ISMS 2022 goes on online. And so these panels are so good that there'll be students, there'll be people that need this information. Please refer them to the Rice Baker Institute website where these are going to be available. I do think I would like to thank George Abbey for his quiet and effective leadership and keeping all of this held together. He does a fantastic job. The staff and the leadership at the Baker Institute do a fantastic job, and they deserve our thanks. Looking forward to next year, we would really like to have people be able to get together at the Baker Institute on the Rice University campus and possibly have a blended meeting that would help our colleagues across the pond in Europe or in Russia. And so we're hoping to have a little bit different format next year if possible. Steve, did you want to say something else? Go ahead.
Oh, I think we'll wrap it up. Richard,
Okay.
Thank you, Bob Thirsk, for your question. I'll go to email on that. Thank you, panelists, and thank you, participants in the virtual meeting here today. It's been fascinating, lots of great ideas, and we'll continue it by talking about a workshop and also hopefully meeting in person next year at the Baker Institute. So thank you, Mr. Abbey, for being our guiding star, and for Richard for being our host today. Thanks, everybody.
Thank you so much, Stephen. We'll see everybody next year.